As we begin our discussion of Chapter 7, we're going to go back to reactions and bring in a lot more of our mole discussion from previous chapters. So we'll see not only now can we define molecules, we can start to see how they react, and then we'll be able to actually quantify things in a chemical reaction. Within this chapter, you're going to get to know your calculator very, very well. There are still some definitions, and we'll see those definitions as we begin here. Investigating our chemical reactions, but a lot of this chapter is calculation intensive. Let's start with a few basic definitions. We're going to talk about in a reaction, what defines a chemical reaction. It's either a physical change or a chemical change. And so when we write a chemical equation, it doesn't have to be molecules breaking apart. A physical change is one where the actual substance composition does not change at all. It's more of a physical change. So things like going from a liquid to a gas, or a solid to a liquid, melting, boiling, condensation, going from a gas to a liquid. So whenever we see a reaction where the atoms or molecules do not change their chemical identity, H2O, water is water, whether it's a liquid or a gas, that's not changing a chemical identity. It's changing the state of that matter, which is still a reaction. There is still a process that needs to be taking place, but it's a physical change process. So the best reaction we can see for this is a physical change, is a change in the physical state of an atom or a molecule. With evaporation, this is our example here where our little carafe filled with water liquid is heated up in order to get the water molecules to boil and evaporate to form water vapor. That still requires energy. It is still a reaction. It's just a physical change. On the other hand, a chemical change of matter is one where the actual chemical composition is changing. Those are the ones we tend to focus on most in this section, where something like iron, which is a solid, reacts with oxygen gas and it forms iron 3 oxide, which is a solid. Rust. So the actual idea of rusting takes place when iron atoms, we see up here, the iron atoms are formed in a semi-latticey type structure. This was the metallic bonding that is known but not often explained in general chemistry classes. But iron atoms form a solid structure. They react with oxygen in the air. And when that reaction occurs, the atoms actually rearrange. The bonding changes. We go from an element of iron and an oxygen diatomic molecule, and now we make an ionic bond between an iron +3 ion and an oxygen -2 ion. So electrons are actually exchanging. The composition, the chemical composition of the reactants is different from that of the products. And these are the reactions that we tend to focus our attention on. Not that you'll never see a physical change occurring, just when we start doing a lot of math and a lot of quantification of chemical reactions, we focus on chemical changes rather than physical changes. In general chemistry second semester is when we focus a lot of theoretical and conceptual ideas on our physical changes. So where these come from is the idea of properties. We have physical properties and chemical properties. Now, a physical property is going to be one that is displayed by a substance without changing its composition. So I want you to think about what types of properties can a substance exhibit without doing an actual chemical change, doing a physical change? These physical properties are related to the physical changes. So take a minute, think about some ideas here. Pause the video if you need to. Come up with some ideas of physical properties, things that would be displayed without changes of composition, changes in phases, of course, or just sitting in a beaker on a table. What could you see if you imagined 1 liter of water in a beaker, liquid, room temperature? What type of physical properties does it have? A few that should come to mind would be odor, not highly recommended unless you're absolutely sure it's water. Taste, color, water is clear. The ones that are attributed to those physical changes could be melting point or boiling point. These are important because they establish the temperature at which the phase change happens. Another one that might not be in the forefront of your mind, but it is useful and we've used it before, is density. Density is an intensive property. It's something that does not matter with that sample size. All of these are intensive properties, meaning that an intensive property is one that is established and is not dependent on a sample size. So if we think about 1 liter of water, we could say that it's odorless, it tastes like water, its color is clear, it melts at around 0 degrees Celsius and it boils at 100 degrees Celsius and its density is 1.0 grams per milliliter. The same can be said for a 1 milliliter sample of water, right? It's the same odor, the same taste, the same color, the same melting point, the same boiling point, and the same density. So a lot of physical properties are intensive properties as well. A chemical property is one that is displayed with chemical changes. So when we look at a chemical property, it's usually displayed only when we see a substance undergo a chemical reaction. Things like flammability, things like acidity. We're going to discuss acidity or being acidic in Chapter 8. Corrosivity, toxicity. These are just some to name a few. Water is non-toxic. Hydrogen peroxide in certain amounts is toxic. Things like acids are corrosive. Bases tarnish, right? They are not corrosive. They don't destroy metals like acids do. So when we think about the actual reaction that's happening there, it's a chemical reaction. Flammability, combustion. A fuel reacts with oxygen to produce carbon dioxide and water vapor. So when we think about all of these, they should be linked to a chemical reaction, a chemical change. And so we want to be able to identify these 2 types of properties along with the 2 types of changes as well. Now, like we said, chemical reactions, what we usually see are chemical changes. They're going to be reactions that involve chemical changes in this discussion. And they will result in new substances. And what we call those new substances are products. We will always see that reactants are going to be the items on the left-hand side. products will be the items on the right-hand side. That will always, always be the case for us. So we read chemical reactions the same way we read a sentence, from left to right. We'll start on the left and we end up with things on the right-hand side. Now, a chemical reaction is a written statement. It's learning a new language. In chemistry, we often think about it in terms of a chemical reaction, in terms of an actual written language. We need to understand its symbols. We need to understand the meaning behind all of the superscripts, subscripts, states of matter. What does the yield sign mean? And so what we are going to be doing is trying to get used to these statements and understand the language of chemistry. You've been learning a lot. You've been building up by the atoms and their atomic symbols. Now you know their molecular formulas or their formula units. So we're building up the words. Now we're going to be putting them into sentences. So when we write a reaction, we should be able to read left to right. We should be able to read whether it's a molecule, or if it's a compound, or if it's an element. We should be able also, if you notice right here, the states of matter. G for gas, L for liquid, AQ will be for aqueous, we'll see that in just a second, and S would be for solid. These are important for us so that when we actually do these things in the lab or try to understand how we would measure these. Are we going to measure gases in grams? Well, to start off with, but remember, we just came from the gas law chapter that says oftentimes we use PV equals nRT. We'll see that later in this chapter, that we can integrate the states of matter into how we quantify the matter. So looking at this reaction, CH4, that's an organic compound. It's usually called a hydrocarbon because it has hydrogen and carbon. CH4 has the common name of methane. You won't need to know the common names of organic molecules in this class. You'll need to know them later on if you take organic chemistry. But right now we would just call this first molecule written CH4. It reacts with oxygen diatomic to produce carbon dioxide and water. We'll use the common name for water. Now, how did this 2 appear? And how did this 2 appear? That is what we call balancing chemical reactions. Let's investigate how we would balance a chemical reaction based off of just being given CH4 and O2 react to form CO2 and H2O. Balancing chemical reactions is important. This sentence right here does not describe a complete sentence. This would be like missing some adjectives or missing some articles in a sentence in English. So what we need to do is balance. We need to look on the reactant side and count up how many carbons, oxygens, hydrogens, how many do we have? And we need to be able to compare it over here to the product side. Because what we do know is from Lavoisier. Remember, Lavoisier way back in the day studied these combustion reactions. He studied them because he understood the development of the law of conservation of mass. Whatever you have on the reactant side has to be equal in mass to whatever is on the product side. Matter can neither be created nor destroyed, but it can be transferred. So when we're looking at the reactant side, I have carbons, hydrogens, and oxygens. I better see carbons, hydrogens, and oxygens on the product side. What I want to make sure in balancing is that there are the exact same number. We can't start with 5 carbons and then end up with 3 at the end of the day. Where did that carbon go? It can't go anywhere. It has to still be there. It might not be bound to hydrogen anymore. It might be pairing up with oxygens, but it's still going to be the same mass of carbon on both sides. So instead of using the atomic masses or the molar masses, what we're going to just do is a simple counting of atoms. Now, I look at carbon and I say, well, I have 1. So I'm going to write 1 right there. I look at hydrogens, I have 4. And finally, I'll look at oxygen, I have 2. There's my count of atoms on the reactant side. Now do the same process for the product side. I have 1 carbon, I have 2 hydrogens, and don't forget, oxygen appears on 2 different products. So when it appears on 2 different products, we will add. I have 2 from carbon dioxide and I have 1 from water. So total, 3 oxygens. Now here's a tip and trick of the trade. You don't have to do this, but it makes life a little bit simpler. If you see a diatomic element, balance that guy last. Why? Well, because he's by himself on the reactant side. So if I actually start to manipulate these products and reactants, what you'll see is I'm going to put coefficients in front of the molecules. If I want to take those 4 hydrogens on the reactant side and make 4 hydrogens on the product side, how do I do that? I put a 2 in front of water. That 2, like any coefficient in a math class, gets distributed to every species that I have in that molecule. That means this hydrogen becomes 4. The oxygen now is 2 plus 2, which is 4. Why I like to balance the diatomics last is because by putting a coefficient in front of a diatomic, I'm really only changing 1 atom. That's a great thing to be able to do at the end of the day. Because once I start looking at multiple different atoms on the reactants and product side, it's going to be tricky to say, which one do I start with? Well, at least you know which one you should do last to give yourself less of a headache. Elements that are by themselves or elements that are diatomics are really nice to save for last. Now, carbon was already balanced. Hydrogen, he was the next in my list, so I chose him to balance. He's balanced now. There's 4 on the reactant side, there's 4 on the product side. Now, how do I get oxygen to balance? I have 4 on the product side and I have 2 on the reactant side. I need more reactants, so I put a 2 in front of oxygen diatomic. 2 times 2 is 4. So a coefficient will multiply into the elements that it sees behind it. But if you have 2 elements that are the same on 2 different products, you add them, like what we did with the oxygens previously. So you have to know when to multiply and when to just add. Let's try another one. CO2O3, right? Be very careful with that one. Cobalt 3 oxide reacts with carbon solid to yield cobalt solid and carbon dioxide gas. Very interesting reaction here. What I want to make sure I understand is I have some cobalt, I have some oxygen, and I have some carbon. I have some cobalt, I have some oxygen, and I have some carbon. Let's go ahead and count. I have 2 cobalts on the reactant side, I have 3 oxygens, and 1 carbon. Remember, if you don't see a subscript, it's understood as being a 1. I have 1 cobalt, I have 2 oxygens, and I have 1 carbon. Now, it doesn't matter the order at which you write this list, and there's multiple different ways to attempt these. This is just my way of doing it. I like to make lists. I like to check it out on both sides. And I also like to write my list in order. If I write cobalt first, then oxygen, then carbon on the reactant side, I'm gonna write cobalt, then oxygen, then carbon on the product side, so my brain doesn't have to search too far for the correlation. Okay, again, which one do you wanna do first? Well, this is the time when I see that oxygen is paired up in a molecule or a compound on the reactant side and a molecule on the right-hand side. So I'm going to start with oxygen. Not that it is necessary, but what I do see is that carbon's by itself and cobalt's by itself. So I should probably do those last. Okay, now looking at 3 and 2 here, how do I make them the same? Well, I have to think about a common multiple. 3 times 2 is 6, and 2 times 3 is 6. So let's go ahead and put a 2 in front of cobalt 3 oxide, and let's put a 3 in front of carbon dioxide. Now remember, these get distributed to each element in that compound or molecule. So cobalt 2 times 2 becomes a 4, and carbon 3 times 1 becomes a 3 because it gets distributed. Excellent. I'm just going to erase my arrows so that I can clean this up a little bit so we can see our progress. Again, not necessary, but just keeping things nice and neat. So now oxygen is done. So now I can focus on my other 2 species, which now should be relatively easy because when I put a coefficient in front of the product of cobalt, I don't change anything but cobalt. Wonderful. Put a 4 in front of it, he's done. Carbon, 1 versus 3. Put a 3 in front of that guy, he's done. So there's my final overall balanced equation. Again, this is a process. This is looking at trying to satisfy the law of conservation of mass. Matter can't be created nor destroyed, so however many atoms of each element I have on a reactant side, I have to see those on the product side. We'll see a lot of extra practice in class. Overall, what we want to be able to say is that a chemical equation provides information about a reaction. It's a statement, it's a sentence, just like any other sentence that we say in English. It's a sentence in chemistry. Molecular or ionic formulas of reactants and products will be there. We may say elements. States of the reactant or product have to be there. Gas is G, liquid is L, solid is S, aqueous, which we'll discuss in Chapter 8, AQ. It is a liquid, but it's in a solution. So that AQ literally means it's going to be in a solution. So there's more than one thing going on there. Usually water is understood to be hanging out with that substance. Now the relative numbers of reactants or products molecules are there to tell us these are required. We have to be able to balance to say how many elements or molecules come together to make the reaction happen, and how many elements or molecules am I going to be producing. Now, we can use these balanced reactions as a way to determine weights of reactants and products that can be made. This is extremely important. This is called reaction stoichiometry. And in reaction stoichiometry, what we are going to be able to see is it's a helpful way to think about a starting set of materials. Starting materials are the same thing as reactants. What do we start with in the lab? If I start with 10 grams of oxygen and 5 grams of methane, how much carbon dioxide am I going to produce? Can I guess? Should I think about it? Do I have a container that's big enough to collect that? Or I can say, hey, I want to make 12 grams of carbon dioxide. Well, how much oxygen and how much methane do I need to start with? It's a way of being able to look at a procedure in a chemical lab and say it's based off of that balanced equation. Now, this is what we call quantities, right? In chemical reactions, we're going to be quantifying things. Again, we're satisfying the law of conservation of mass. Matter cannot be created nor destroyed. And we're balancing those equations by balancing the atoms within the equation. So the study of numerical relationships between chemical quantities in a chemical reaction is called stoichiometry. It's exactly what we just did. We counted up how many carbons, oxygens, and hydrogens we had on the left. We equated them to how many were on the right. We balanced it. And we can see even down here in the molecular view, there's 1 methane for every 2 oxygens, and will produce 1 carbon dioxide and 2 water molecules. That number is a quantity that we can take through. If we know the amount of atoms, we technically know the moles. And that is very, very important for us. The mole to conversions in a balanced chemical reaction. Now this one is pretty big. 2 C8H18s, that's octane, react with 25 oxygen diatomic gas particles to yield 16 carbon dioxide molecules and 18 water molecules. Now this stoichiometric ratio acts as a conversion factor. These numbers are so important to us because they are going to be the mole ratios. Mole ratios are extremely important in being able to quantify either reactants or products. Notice that we have ratios between reactant to product, reactant to reactant. If I start with 5 grams, how many other grams do I need to not waste time? Or product to product. If I made 5 grams of carbon dioxide, how much water am I also going to make? So we can get the relationship between any 2 molecules or elements in this reaction utilizing the mole ratios. So we already know that we can take the mass and utilize the molar mass or the atomic mass, grams per mole, to convert from grams to moles. Remember, we use this to be able to find a middle point in the lab, right? Grams are things that we use in the lab, but again, reactions react at the atomic level. So we utilize moles and Avogadro's number to be able to convert something in the atomic mass units to the laboratory units. And so this conversion factor of atomic or molar masses, we will represent. And how we're going to represent it is by looking again at things that we have just discussed. I'm going to start with C8H18 and say, if I start with 5.00 grams of C8H18, how many moles of C8H18 do I have? This is an old reaction or an old setup, an old calculation that we did. And so what we'll want to be able to do is remember all of our lovely molar masses, atomic masses, things like that, because how we go from grams to moles is through the molar mass. The molar mass for C8H18 is 114.26 grams per mole. So when we do this calculation, if you remember, we would want the units that I have in grams to be canceled with grams in the denominator. Units that I want should be in the numerator of that conversion factor. So moles, 1 mole over 114.26 grams. So when we're setting this up, a couple of things to remember. Not only is the number important, but the units as well. And we'll just see a nice trail of our conversion factors later. Once we apply this model that we just did in previous chapters, for one thing, we'll apply it to a whole string in a balanced chemical reaction. So if you have forgotten any of these conversion factors with atomic or molar masses, it'll be good to pause and to go back in your notes. So what we can do is a mole to mass or a mass to mass conversion. We can actually start with the grams of one thing and go to grams of another. Watch. The mass of A cancels with mass, and you get moles of A. The moles of A can be canceled with the moles of A to convert to moles of B using a balanced mole ratio. This would be the mole ratio from the balanced chemical equation. Has to be from a balanced chemical equation. And then those moles of B can be converted to grams of B. So we can actually go from the mass of one reactant to the mass of another substance, whether that's a reactant or product. We can interconvert with masses, but again, the overarching idea there is we have a balanced chemical equation and a mole ratio. Now let's go back to this reaction. We can use our balance from before. 2, 25, 16, and 18. I suggest you go back and practice that one, but we'll probably do it in class as well. Now, octane, C8H18, is a primary component of gasoline, and every year, cars produce about 3.7 times 10 to the 15 grams of, or 3.77 times 10 to the 15 grams of C8H18 is burned by cars on the road. So when that octane is burned, it's a combustion reaction in our cars. And by default, what's coming out of our tailpipes is carbon dioxide, one of the important greenhouse gases that we are looking at to help mitigate and reduce for climate change. So carbon dioxide is not the worst molecule out there that depletes the ozone layer and creates greenhouse gases up in the air, but it's one that we actually produce a lot of ourselves. The number one problem being methane, CH4, which is produced by a lot of having a lot of extra wasteful beef in agriculture. But this one is a nice one to think about because most everybody has had or driven in a car before. We don't often all raise cattle. So when we look at this question, this is a typical question that can be solved by stoichiometry. If we have an amount that we start with, and it reacts to form carbon dioxide, we can say how much carbon dioxide is actually released. So let's walk through this one. 3.7 times 10 to the 15 is where we are going to start. That is our given. What we want to do from there is convert to moles. We need moles of C8H18 to do anything with that balanced equation. I need to divide by grams in order for my units that I have to cancel so that I can get moles. Again, 114.26 grams. Now, I have moles of octane. What moles do I want? Where am I actually going in this reaction? If I start here, I want to go to carbon dioxide. So I will utilize this mole ratio. 16 moles of CO2 in the numerator, that's my desired unit, divided by 2 moles of C8H18. This is the balanced equation, the mole ratio. That is very important for me to understand the reactivity here. And then from moles of carbon dioxide, I can go to grams of carbon dioxide. Make sure all of your units cancel appropriately. Grams of C8H18 cancels with grams. Moles cancels with moles of CH18, and then we'll get our moles of carbon dioxide to cancel, and we're left with grams. Doing the math, we should come up with 1.1 times 10 to the 16 grams of CO2. A lot of CO2. is produced in the atmosphere because of cars. Now, 2 sig figs results in 2 sig figs. All of my unit conversions, all of my molar masses and my mole ratios are actual numbers. Those are infinite number of sig figs. So the only sig figs that you would want to be able to look at are the starting measured value. Now, sometimes in a reaction, we'll see that we have 2 different starting material amounts. If you react 7 grams of SO2 with 2.7 grams of water, how much H2SO4 in grams will be produced? I like this reaction because it's something that's actually real life. Sulfur dioxide is a component in onions, and when you cut into an onion, if you do a lot of cooking, which I do, I have a hungry toddler and a hungry husband all the time, so cutting onions breaks open the cell walls and SO2 gas is formed. It's an actual adaptation that onions have in order to not be eaten, right? What that does, though, why it's an adaptation to avoid digestion, is the fact that when it mixes with moisture and oxygen in the air makes it a sulfate, and then mixes with moisture in your eyeballs, you get sulfuric acid. Ouch! Now, you can be like me and wear safety goggles when you cut onions, and I've never cried with an onion that way. Or you can do some of the old wives' tales where you stick your head in the freezer for a few minutes, or you run the onion underwater. When you run the onion underwater, it actually does help after you cut it, because you're taking the sulfates that are produced and washing that sulfuric acid down the drain, which is totally fine and much better than reacting with the moisture in your eyeballs and creating it in your eyes. But again, let's go back to the chemistry. If you react 7.00 grams of sulfur dioxide with 2.70 grams of water, how much H2SO4 in grams will be produced? Now, I have to define a few things. We have 7.00 grams and 2.7 grams. What do these mean? Are they all going to be used up? Why did I measure both? Well, in the lab, you tend to measure 2 things. So what we have to be able to say is, of these reactants, there will be one that is limiting, and there will be one that is in excess. The limiting reactant, or also called the limiting reagent, is going to be the reactant that is completely consumed in a chemical reaction, and it limits the amount of product. The reactant in excess is the reactant that's going to have a greater quantity. Now, I can't just look at 7 grams and 2.7 grams and say that sulfur dioxide is excess. But what I can do is start to think about looking at the mole ratios. At the end of the day, these questions are all going to be geared towards a theoretical yield. How much product can I theoretically make in the chemical reaction based off of the limiting reactant? That's going to be the very important part. All of these conceptual definitions are interacting with each other. The limiting reactant will tell you how much product you have made. The reactant in excess is going to be partially used up and partially left over. So let's revisit that calculation again. Now, I can't straight off the bat say that 7.00 grams of SO2 is bigger than 2.70 grams of H2O, and therefore it's excess. What I have to do is start to compare apples to apples. Right now, I have 2 different molecules masses, so that's comparing apples to kiwis. What I want to get them to is moles of the same thing, moles of H2SO4. Then I can say, in the comparison here, which one is my theoretical yield? Now, the theoretical yield will be the one based off of the limiting reactant. So let's go ahead and try that out. 7.00 grams of SO2. I need to convert it to moles. 1 mole of SO2 divided by its molar mass, which is 64.06 grams. Now let's go back to that balanced equation and look at our mole ratios. 2 moles of H2SO4 divided by 2 moles of SO2. Now when we're looking at that value, I like to stop here at the moles. You can go all the way to grams, but again, you're just trying to get to some sort of apples to apples comparison. So we see if all of the 7.00 grams of SO2 was used up, we would produce 0.109 moles of sulfuric acid. Let's compare that to the 2.70 grams of H2O. 1 mole of H2O is 18.02 grams of H2O. Again, the mole ratio, 2 to 2. Makes it nice and easy. You can also use the 1-to-1. You can reduce that ratio if you wish. I like to keep it just the same, again, so that my eyeballs don't have to do so much work. And we get 0.150 moles of H2SO4. Now let's compare these values. I can either make 0.109 moles or 0.150 moles. When looking at this, the smaller is the maximum amount I can make. Why? Because it's limited. It's limited by our SO2. Yes, we have an excess amount of H2O that we can utilize if we had more SO2 gas, but we need to focus on the limiting reactant or the limiting reagent. So what we have learned from comparing these two numbers, the limiting reagent is the one that produces the smallest amount of product, and that is SO2. The excess reagent or the excess reactant is the one that could produce more, but it's not going to because of the limiting, and that excess reagent is water. The theoretical yield is the maximum amount that I could produce, 0.109 moles of H2SO4. Let's go ahead and put that into grams like the question states. All I would want to do is multiply it by 98.08 grams of H2SO4 over 1 mole of H2SO4. And that equals 10.7 grams H2SO4. Now, when I look at these, what I want to be able to just understand is this idea that if I was to take two starting materials and ask for a product, one of those starting materials is what I'm going to base my answer on. The limiting reactant is what you want to base your answer on. The excess reactant is important to know. We can see how we can figure out how much is left over. We'll be able to use stoichiometry to go back and forth, seeing all different sorts of things based off of what a question is. And we'll have a lot more practice in class. But what you need to be comfortable with is comparing apples to apples, converting using stoichiometry to get two different starting materials into the same unit. We chose moles of the product, moles of the answer. Now, you can do this in a variety of different ways, but this to me is the most straightforward way. We'll investigate other ways in class. Now, the actual amount is quite different than the theoretical amount. The actual amount of product produced is something that you would actually obtain in the lab. And we can calculate from that actual amount and from the theoretical yield something called a percent yield. Now, this is an efficiency. How efficient was the reaction? Now, in chemistry, not everything is perfect. I know it may seem so, and it may be a wonderful, amazing subject, but a percent yield tells us, did the chemistry actually work the way we wanted it to? Did we let the reaction stir long enough? Did we heat it well enough? So when we're in the lab, we might not always get the theoretical yield. The theoretical yield is a calculation-based answer. An actual answer could look like this next subsequent hidden part number B or letter B. If 9.51 grams of H2SO4 is actually produced, what is the percent yield for this reaction? Well, my percent yield is going to need both the actual divided by my theoretical times 100%. And that's where we'll be able to see the efficiency of this reaction was 88.9%. And for a chemistry reaction, that's actually not half bad. Yeah, and some of you might be thinking, damn, a B+, that's not great. But in chemistry, that's pretty good. Now, typically, this ranges from anywhere between 20% and 95%, right? It's very rare that we see anything up in the high 90s for a percent yield, unless it's an extremely reactive reactants. And the products are extremely stable. You might see some of those theoretically on an exam question or a practice problem, but when you get into the lab, and if you've been there, you'll probably know it doesn't always happen that way. So, chemical reactions, just to summarize, the reactions will have with multiple reactants where we get many different starting material masses. It's likely that one of those is going to be the limiting reactant and someone's going to be in excess. So we do need to calculate a theoretical yield based off of comparing those reactants. So even if you think the numbers might seem small or the number might seem big, I'll just look at them. Please make sure you're comparing apples to apples in that theoretical yield category. All right, to just end our discussion here, I want to talk about the types of reactions that we've seen today, or the types of reactions that we're going to also see in the next chapters. Combustion reactions. By definition, a combustion reaction is some sort of fuel, usually a hydrocarbon, so something that has carbon and hydrogen. You can also see oxygen incorporated in that, or nitrogen. Fuels can be more complex than just hydrocarbons, but they react with oxygen to form carbon dioxide and water. Those three components are going to be consistent. So when you see that type of a setup, you should understand it's a combustion reaction. Now, we do also have formation and decomposition reactions. They are exactly opposite of each other. A formation forms 1 mole of one product. A good example we can think about is this reaction. H2 and O2 yield H2O2. Hydrogen peroxide is made from its elements hydrogen and oxygen as found in nature. They are diatomics in nature, so therefore that's a good example of a formation reaction. A decomposition reaction is the exact opposite. When we take one product, 1 mole of one product, and we make it into its elements. Something like, let's just do the reverse of rusting. Iron 3 oxide is made up of iron and oxygen diatomic. Don't forget that you're going to have to balance it. And what's important is the definition of 1 mole of one reactant is understood. We won't put a 2 in front of that Fe2O3 to balance in whole numbers. What we'll do is we'll use fractions in the coefficients of the products because we are understanding the definition of 1 mole of one reactant. The last one, the last set of definitions or reactions that we're going to see are displacement reactions. They could be double displacement or single displacement. These we will investigate more in the next chapter. A double displacement is going to be two usually ionic compounds interact together, the outer two and the inner two switch places. They do a do-si-do. It's the cation of one reacts with the anion of the other, and the anion of the first reacts with the cation of the second. So they're really swapping ionic partners. Now for a single displacement, usually what happens is one lone solid, usually something like sodium metal or carbon solid. It could also be a diatomic, something like chlorine gas, reacts with an ionic compound and produces one ionic compound and another lone or single element. And so we'll see that not all partners get paired up at the end for that single displacement. For these types of reactions, what's important for us right now is just to identify and be able to look at a reaction, balance it, maybe do some stoichiometry, and can you slap a label on it? What is happening here? I think that's the best way to get the real life application and to start seeing what the balanced chemical equation can do for you in terms of understanding the sentence involved, the chemistry language here. This wraps up our discussion of Chapter 7. Thank you so much for joining me.